Welcome to another episode. In this video, I'm going to show you guys how useful the Laplace transform is. So let's go ahead and get started with an example. So we're going to solve this ODE. So the ODE that we're going to be solving, on the left we have x prime, and on the right we have the Heaviside function. And from last time, if you guys remember, the Heaviside function is just without the a. So when a is equal to 0, what we're looking at, it's equal to 0 when t is less than 0. But at 0 and greater, the function is 1. So when we shift it by a, let's imagine that a is somewhere here. All we're doing is just shifting the entire graph. So this is what we're looking at. So let's go ahead and solve this ODE. Let's see what we get. And let's see how the Laplace transform is useful. So the first thing that we need to do is, in all of these, is we're going to take the Laplace transform of both sides. Last time we calculated the Laplace transform of the Heaviside function. So we know what that equals. So this time, what we need to do is we need to calculate the Laplace transform of the left. So let's go ahead and do that at this moment. So we're assuming a few things. So first of all, x is differentiable, otherwise you can't take its derivative. So this is the definition. Nothing has changed. Then we use integration by parts. So here comes the tricky part. We want this limit as t goes off to infinity to go to 0. So we want x to be of exponential order. So once that goes away, what we're ended up with is just x evaluated at 0 minus, so there's a double negative, so that becomes a positive, the Laplace transform of x. So if you pull this s out here, notice what remains. It's the Laplace transform of x. So let's go ahead and call the Laplace transform of little x, capital X, of s. And then there's an s on the outside here. Okay, so that is the left. What about the right? Well, last time from our previous episode, we calculated that. Let's go ahead and zoom up. And actually, last time, this should have been an a. So let's go ahead and copy. And we're going down. And since we took the Laplace transform of both sides, we're going to paste it on the right. So then we have this here. So now we want to solve for capital X. First of all, we have initial conditions. And one of the initial conditions is that at x, our function goes to 0. So that vanishes. So now what we have here is the Laplace transform of our function x is equal to e to the negative sa over s squared. Nice. Now, how do we get our solution? Well, you want to take the inverse of the Laplace transform. There's actually a couple theorems. When f is continuous and of exponential order, the Laplace transform exists and is unique. So we have invertibility. So if we can find, our goal is to find a function. So let's go ahead and, well, it is going to be lowercase l. So we want to find, let me do this in the pink. We want to find lowercase x such that when you put the Laplace transform, you're going to get this here on in the circle. So that's our goal. So we want to find such an x. Well, there's a lot of formulas that are helpful, and one of them is the shifting property. So take a look at this in the box here. So the shifting property, you have the Heaviside here, and then you just have any function here that is also shifted. And on the right, well, what do you get? You get e to the as, and you also get the Laplace transform of f not shifted. So this is useful because take a look at what we were trying to figure out. There's an e to the negative s at the top right here. So this is going to be useful. So taking a look at this, what we want to look at is the function 1 over s squared. So there are tables, and this is a function that we actually worked with last time, and the Laplace transform of t is this here. So let's go ahead and try to plug things in so that we get what we want. So we want, let me start erasing some items here. We want an s. We want this s here. So let me go ahead and erase this box that I got going on. And so we have e to the negative as, this is what we want, times 1 over s squared. Well, we know what kind of f gives us that, so let me go ahead and erase this and just put it in. It's t. Okay, carrying that through, the function t, I plug in t minus a, and I get that. Interesting. So therefore, when I take the inverse, so of the Laplace transform, the inverse of the left, it's going to equal to the inverse on the right. What I'm going to get is that x of s, not of s, but of t, is going to be t minus a times the heaviside function shifted. And that is our solution